Welcome to the video on the Taylor theorem and Taylor polynomials. And we've actually already touched on this. When we did the videos on approximating functions with polynomials, we used Maclaurin's series, which is actually a special case of the Taylor polynomial or the Taylor theorem. And we approximate the function around x equals 0 when we did the Maclaurin series. But in general, you could approximate a function around any value. And so, and if you do it around something other than 0, it's kind of the more general case, and we're dealing with the Taylor polynomial. So what is that? So let me just write the definition down, and then we'll do a couple of examples, and then we'll graph it to get the intuition. So a Taylor polynomial says that if I have a differentiable function f of x, and I want to approximate it with a polynomial at c. So at some value of x equals c, I want to approximate this function. So let me just draw a quick and dirty one, and we'll actually draw an accurate one later. So let's say that that's my axes. This is my function, f of x. So I could pick some value c, some value x is equal to c. Maybe it's right there. So that's c. And I would want to approximate it. I would want to create a polynomial that can approximate the function around this point. And the Taylor theorem tells us that the Taylor polynomial to approximate this is, and then I'll give you the intuition for it in a second, p of x. And this looks really complicated, but when you do some examples, you'll see it's not so bad. P of x is equal to f of c plus f prime of c times x minus c plus f prime prime of c over, they say 2 factorial, which is just 2, but I'll write 2 factorial. They do that so that you see the pattern that emerges. This is over 1 factorial, really, and this is over 0 factorial, really, times x minus c squared plus, I'm already running out of space, f the third derivative. I think at this point people just write a 3 in parentheses of the function evaluated at c over 3 factorial times x minus c to the third. And you could just keep adding terms. You could go on like this for infinity. But let me give you the intuition of what this is. And then let me just show you, just to hit the point home. So then you could plus the fourth derivative of the function evaluated at c times over 4 factorial times x minus c to the fourth. Now what's the intuition? So first of all, what happens to this polynomial at c? So what's p of c? P of c is equal to, well, if p of c, everywhere where you see an x here, you have to put a c, right? So this term would be c minus c, so that would go to 0, or it would be 0. This term would be c minus c, it would be 0. This term would be c minus c, so it would be 0. This term would be c minus c, 0. And all you'd be left with is this f of c. So great. We already know that at least at the value of c, the polynomial is equal to the function. So it's going to intersect this line, right? And actually, if we just had a Taylor polynomial with just that first term, what would it look like? Well, it would just be a horizontal line right there. So it would be a pretty bad approximation. But what does this second term do us? Because we know that when we just evaluated c, all these other terms just drop out. So what do they do for us? Well, the second term actually ensures that the derivative of this polynomial evaluated at c is equal to the derivative of this function evaluated at c. What do I mean there? Well, what's p prime of x? P prime of x is equal to, well, this is just a constant term. It might look like a function, but it's a function evaluated at c, so it's just a constant term. And so that's 0. And then what is this? What's the derivative of this? Well, the derivative, we could use, this is a constant term, and this is the derivative of this is just 1. So you could almost just view this as f prime of c times x minus f prime of c times c, which is a constant, whatever. So the derivative of this expression is f prime of c, and then plus the derivative of this expression, and that's equal to what? 2 times 2 divided by 2 factorial, which is just 1. So it's f prime prime of c times x minus c, and then plus, let's see, 3 over 3 factorial, so that's 3 over 6, so we'll just have a 2 in the denominator, f prime 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 of c over, what is it, 2 times x minus c to the squared. And you don't have to worry about all of this. And we could just keep going, but I wanted to show you one thing. What is p prime at c? P prime at c. What is the derivative of this polynomial when you evaluate it at c? Well, when you put c into this derivative function, all these other terms are going to drop off, and you're just left with this one. You're just left with this one, because these x minus c. Sorry, I just had some walnuts. I should have had some water with it. If you put the c here, they drop out. So the derivative of this function evaluated at c is equal to f prime of c. So as you can see, this Taylor, what's neat about this Taylor polynomial is it's equal to the function at c. Its derivative is equal to the function at c. The second derivative is equal to the function at c. And every term you add to the Taylor polynomial actually makes it so that, that term derivative is of the polynomial evaluated at c is equal to the function. Hope I didn't confuse you. The big picture is the whole thinking behind, I guess, what Taylor thought of was, wow, I can construct, if this function is infinitely differentiable, meaning that I can take the first, second, third, fourth, all the way to infinitieth derivative of this function, I could construct a polynomial like this, and I could just keep going by adding more and more terms, so that this polynomial's, zeroth derivative, which just means the function, the 0, first, second, third, fourth, all of this polynomial's derivatives are going to be equal to the function, at least around that point. And actually, we'll see that there's actually a whole class of functions that the Taylor polynomial, if you were to take the infinite series, is actually equal to that function at all points. But anyway, and actually I talked a little bit about that when I proved that e to the I pi is equal to -1, which to me was the most amazing the result in mathematics, whatever. But whatever. This might have been a little confusing for you, so let's do a particular example. The particulars are always the more fun. I think when you see me do an example, you'll see that it's not so bad. I'm even going to erase this fourth term. So let's approximate, I don't know, cosine of x. So let's say that f of x is equal to cosine. Let me do it in a different color. We want to approximate f of x is equal to cosine of x. And let's pick some arbitrary number. Let's not pick some numbers that works well with trigonometric functions. Let's pick around, or let's say c is equal to 2. No, or 1. So we're going to approximate cosine of x around 1. So what is the Taylor approximation, or the Taylor polynomial? Well, we could just chug through this one. P of x, I will do it in yellow. P of x is equal to f of c. So the function evaluated at c is just cosine of 1, right? Plus f prime of c. Well, what is the derivative of cosine of x? It's minus sine of x, right? Minus sine of x, and we will have to evaluate it at c. So it's minus sine of 1, right? C is 1. That's what we're approximating around, times x minus c. And then plus the second derivative. Plus the second derivative of x. Well, what's the second derivative? Well, it's going to be the derivative of minus sine, which is minus cosine of x. So it's minus cosine, but we're evaluating it at c. So this is actually going to be a number, right? So c is 1. Cosine of 1 over 2, right? 2 factorial is just 2, times x minus 1 squared. Oh, sorry, this should be a 1. Right? I said c is equal to 1. Times x minus 1 squared. And let's keep going. Plus the third derivative. Plus, what's the third derivative of cosine? Well, it's the derivative of minus cosine, so that's plus sine. So plus sine evaluated at 1, sine of 1, divided by 3 factorial, so that's 6, over 6 times x minus 3 to the third. Sorry, my brain is really, I ate too many walnuts. Undo, edit, undo. X minus 1 to the third, right? And then let's do one more term, just for fun. So then we're going to take the fourth derivative, which is the derivative of the third derivative. So the third derivative was positive sine, so now we're going to be plus cosine evaluated at 1 over 4 factorial. What's 4 factorial? It's 3 factorial times 4. So over 24 times x minus 1 to the fourth. And we could just keep going. The fifth derivative over 5 evaluated at 1 over 5 factorial times x minus 1 to the fifth. And just keep adding, but then it'll take us forever, etc., etc. So what does this thing look like? And what I'm going to do is I'm going to show you how this polynomial develops as we add terms. So let's see. I have this graphing calculator that so this thing I got from, just to give them credit, it's my.hrw.com. And this is the graph of cosine of x. So just the first term here, cosine of 1. If we were to just graph the first term of this polynomial, what does it look like? So I'll just type in cosine of 1 and graph it. So there you go. Just the first term of the polynomial. If all of these terms, these other terms weren't here, the polynomial would just be a constant, right? Cosine of 1. And it's a pretty bad approximation, but at least it equals the function at this point. So it gives us something. But let's add some terms. Let's add the second term to it. So what was the second term? It was sine of 1 minus sine of 1 times x minus 1. So let me add that. So minus sine of 1 times x minus 1. Graph it. There you go. So this is neat. So when you just added two terms, what did we say? The function will equal, the polynomial will equal to the function at our x equals 1. And now the slope is also equal to the function. The slope of the polynomial is also equal to the slope of the function at x is equal to 1. So this is a better approximation. At least if we stay pretty close to our chosen c, it's a decent approximation for the function. Now, obviously, if we get far away out here, this is a horrible approximation for the function. But let's keep adding terms. And as you can see, I just want to show you that I'm just typing in the actual terms. So let me type in the next term. I want to, just so you believe that I'm doing it. So the next term, well, I have to see it. So let me type it in. So the next term is minus cosine of 1 divided by 2 times x minus 1 squared. And let me graph it. Okay. So now, just to show you, I just typed in the second term. And now let's look at the graph. Now this is neat, right? So the first term got us a horizontal line that just intersected the point at cosine of 1, and it was a really bad approximation. Then, when the second term made sure that at least the first derivative was the same, and so then the line was just essentially the tangent line when we only had two terms. Now the third term makes sure that it makes sure that the second derivative of our polynomial at x equals 1 is equal to the second derivative of the polynomial of the function. And notice that this green graph is concave downwards, right? Which means that and so is the function at 1. So this is pretty neat. We're getting a little bit, so it's kind of approximating the curve here. It's getting a little bit better. Remember when we went out far to the left, it's starting to approximate the function better around here. It's closer at least, right? The last time the line just went up, and here it was a really bad approximation. But let's add another term. Let's add our third term. Our third term, I can see it. It's right there. So plus sine of 1 divided by 6 times x minus 1 to the third power. just to show you, I just typed it in right there. X minus 1 to the third power. And let me graph it. That is neat. Just with 3 terms on our polynomial, well, actually, what? That was, right. Just with 3 terms, well, actually, that's the 4th term, officially 1. But the first term was essentially, well, anyway, you get the point. But we're already starting to approximate this pretty well, right? Now the third derivative is equal to, the third derivative of the polynomial is equal to the third derivative of the function at the point x equal to 1. And we haven't even studied third derivatives. That's kind of like the concativity of the derivative or whatever. But as we can see, it approximates the function even better. Obviously, though, when we go further away, it starts to break down again. But pretty close. If all you saw is from here to here, it'd be hard to tell them apart. Let's add that last term we calculated. And this should be pretty neat. Let's see. The last term. Plus cosine of 1 divided by 24. And notice every term, the scaling factor, right, here is 1, then 1/2, then 1/6, 1/24. It becomes a smaller impact on it. And it only starts to matter as you move really, really far away from your chosen c, in this case 1, right? The further out you go, when you're close to your point that you picked, these other terms don't matter much, right? Because you're doing 1/24 and then 1/5 factorial, et cetera, et cetera. But as you get further and further away, these terms become more significant, right? As x gets further and further away from 1, and then that's where these start to play in, and you see that in the approximation. But anyway, let me graph it. So cosine of 1 divided by 24 times x minus 1 to the 4th. Let me graph it. Even neater. And if you have some spare time, you might just want to keep adding terms to this. So that's all the Taylor polynomial is. And I realize this is probably one of the longest videos I've done. I'm pushing 17 minutes. It's a little confusing at first because they give you this huge formula, and they give you the c, and you're like, what is that c, and how do I take the derivative? But when you actually try to chug through it, you just have to realize, oh, all this is saying we are constructing a polynomial that at some point c that we've picked, this polynomial's 0th, 1st, 2nd, 3rd, 4th, 5th, and so on derivative is going to be equal to our function. And actually, if we did, if we did 10 terms, or if we did all of the derivatives, these would start to actually equal each other. So hopefully that didn't confuse you. I know it's kind of when you see the formula at first, it can be kind of daunting, and especially sometimes it's even more daunting when someone even explains it to you. But hopefully that gave you some intuition. If it didn't, ignore this video. See you soon.